So now we're going to look at a few examples where we use the rulebook for the derivative to compute derivatives. And let's just first quickly recall what's in the rulebook for the derivative. So it says that if f and g have a derivative at a point x, so let's say are differentiable at x, then f plus g derivative is equal to f derivative plus g derivative. F times g derivative is equal to f derivative g plus f g derivative. So notice that while all of these rules come from the corresponding rules for the limit, they are slightly more complicated. And to understand why, you would have to look at the proofs. But right now, we're just going to apply them. We have the quotient rule, which looks like this. So you need to take f prime g minus f g prime, and then g to the square. And we have the composition rule, or chain rule, as it's called, where if you take the derivative of such a thing, what you get is the same as if you took the derivative of f first, and then insert the g of x into that expression, and multiply this with the derivative of g. So here I'm taking the derivative of this full expression here. And the chain rule can be slightly annoying to decipher sometimes because we rarely write out that parenthesis around the entire expression. But here we really mean to find an expression for this first, then take the derivative, and here take the derivative of f and then plug in g multiplied by the derivative of g. So these are our rules. Let's now take them out for a little spin. So first, let's do the derivative of, oh, and I should mention that writing d dx or the prime here means exactly the same thing. So here, if I just want to use the prime, I could do this. But it looks a bit ugly, so here people prefer the d dx. Up here, it's just faster to write the prime everywhere, so using the d dx is less typical here. And now when we're looking at the first example, which would be this thing here, then I can either write this for its derivative, or I can write this for its derivative. It means the same thing. So now when we compute this, we use the summation formula. So this is the same as if I do d dx x to the third plus d dx sine x. So what is the derivative of x to the third? Well, from high school, you should know it's 3x squared. And what's the derivative of the sine? Well, from high school, you should know it's the cosine. Both these formulas will be proven in this course. This one is just a simple exercise. This one requires a bit more effort, but they should be familiar to you from high school. And let's now take the second example. So up here, the point was the summation rule. Now it's the product rule. So I'm using this thing here. And this now would be d dx x to the third times sine x plus x to the third. And let me not write d dx here since it just takes too long. This is fine. But this is also a bit dangerous because it may seem as if you're taking sine to the power 1. So it's an aesthetic choice. Do I do d dx or do I do the prime? Rarely you use both like this. So here I'm mixing a little bit just to acquaint you with the notation. Anyway, here is 3x squared as before. I keep my sine x. Here I have x to the third, and I get my cos x, like this. For the next example, I do 1 over x to the third sine x. And when you do the rule book, it's quite common to do the reciprocal rule separately. So it looks like this. And when you prove all these rules, you usually first do the reciprocal rule, and then you combine it and the product rule to get the quotient rule. But you don't have to go around remembering this guy. It's enough to remember him, because if you put f equals to 1 here, you get the reciprocal rule as a consequence of this. So if we were to do this using the quotient rule, how would it look? Well, first I'm taking the derivative of 1, then I'm keeping this guy here, then I'm doing minus, and then I'm doing 1 times the derivative of this thing here. And then I'm dividing all of this by x to the third sine x to the square. And please note that the derivative of a constant is 0, so this guy has 0 as its derivative. So all of this just dies. And unsurprisingly, what's left here is just what you would get if you had used the reciprocal rule. Now, to take the derivative of this, I used the product rule. I already did this in the previous line. So now this is just 3x squared sine x plus x to the third cosine x divided by x to the, well, 6 sine squared x, like this. And I mean, you can be happy with this answer if you want. It's a bit untidy to do it like this because we have a bunch of x's here that you can cancel. So this would be 3 sine x plus x cos x divided by x to the 4 sine square x. Now, that's probably a more tidy way of giving this answer.